Okay, back to the pizza delivery example. Suppose the researcher wants to use alpha equals zero point zero 0.05. Then the rejection region will be reject H naught if p-value is less than 0.05. Since our p-value is 0.0057, we just found that in the previous slides, this is less than 0.05, so we conclude then that reject H naught, there is sufficient evidence to conclude that the mean of all delivery times is less than 30. And this supports the restaurant's claim. So this is the conclusion. Um, this is step 4. If the p-value was greater than 0.05, we would conclude that we fail to reject H naught. There is insufficient evidence to conclude that the mean of all delivery times is less than 30. But since our p-value is less than 0.05, we reject H naught. So for every hypothesis test, there are two possible conclusions. That's reject H naught or fail to reject H naught. If we reject H naught, that means there is sufficient evidence to conclude that whatever the alternative hypothesis says. If we fail to reject H naught, that means there is insufficient evidence to conclude that whatever the alternative hypothesis says. These are the only two conclusions for a hypothesis test. Reject H naught, there is insufficient evidence of the alternative, or fail to reject H naught, there is not sufficient evidence of the alternative. So let's do a second example. Suppose that the mean weight of all newborn babies in the US is 7.4 pounds with a standard deviation of 2.3 pounds, which is the population standard deviation. A study was conducted of babies born from women with gestational diabetes, which tends to increase the weight of a baby. So, of the 35 babies in the study, the average birth weight was 8.1 pounds. And they want us to use alpha equals 0.01 to determine whether the average birth weight of babies whose mothers suffer from gestational diabetes is higher than the national average. So the first thing we do is set up the hypotheses. So we want to see if the population mean of babies from mothers with gestational diabetes is greater than the overall population, which is 7.4. So our alternative is mu is greater than 7.4, meaning our null hypothesis is mu is equal to 7.4. Then we plug in the values for the z-test statistic. Our sample mean is 8.1 minus the hypothesis value, which is 7.4, divided by sigma, which is 2.3, over the square root of n, which is square root of 35. And we get a z-statistic is 1.80. And the alternative hypothesis here is greater than, so the p-value will be the probability that z is greater than 1.80. So whatever our alternative sign is here, that's what determines this sign as well. So we get the sign for calculating the probability equal to the alternative hypothesis sign. So looking up 1.8 on the z-table, the probability is 0.964, but we want above it, so we do 1 minus 0.9641, and the p-value is 0.0359. So this is bigger than 0.01, and our rejection rule is reject H naught if p-value is less than 0.01. So we fail to reject H naught. There is insufficient evidence to conclude that the average birth weight born to mothers who had gestational diabetes is greater than the average birth weight of other babies. So here's another example. the chocolate chip cookie maker wants to have, on average, 10 chocolate chips in each cookie. If the average differs from 10, the maker will recalibrate the machine. A sample of 40 cookies has a mean of 9.1 chips per cookie, and we're assuming a population standard deviation of 2.0. And using alpha equals 0.01 should the machine be recalibrated. So since we have the population standard deviation, we use the z-test and not the t-test. And in this example, there's not a clear indication whether it's greater than or less than, so the alternative hypothesis will just be not equal to. So we have our null hypothesis is mu equals 10, because our hypothesis value is 10, versus our alternative hypothesis, which is mu is not equal to 10. So plugging into the z-test statistic formula again, our sample mean is 9.1 minus our hypothesis value, 10, divided by our sigma, which is 2, over the square root of the sample size, which is 40. So this gives us our z-statistic of negative 2.85. And this is a two-tailed hypothesis since it's not equal to. Remember, in part 1 I said the difference between two-tailed and one-tailed, and this is two-tailed. So we have 2 times the tail probability, which is 2 times the probability that z is less than negative 2.85. So when we do that, we look this value in the table, and we get 0.0044. And since alpha is 0.01, we reject H0 if p-value is less than 0.01. That's a rejection rule. Therefore, we reject H0 since our p-value is less than alpha. And there is sufficient evidence to conclude that the mean number of chocolate chip cookies differ from 10. So we would recalibrate the machine. So there are a couple methods of hypothesis testing. The first way is p-value method, where we calculate the p-value and we reject H0 if p-value is less than alpha. That's the one we just went over. And we will use this method since this method is really used in reality more. So when you read a journal, they're using this method. The other method is, you won't really see, but it's the traditional method in which you use test statistics and not the p-value. But most researchers only care about getting the p-value. In my situations that I have encountered through consulting, the researchers really just want that p-value. So they're not interested in the test statistic. So I'll just mention this briefly, that when you conduct a hypothesis test, it is possible to make an incorrect conclusion. And there are 2 ways this could happen. The first one, we wrongly reject H0. For instance, in the criminal justice analogy, that would mean we are convicting an innocent person. That's called type 1 error. And you can write type 1 error out, but I normally write it like this, but it's the same. And the other type of error is if you wrongly fail to reject H0. In the criminal justice analogy, this would be the same as acquitting a guilty person, and this is called type 2 error. In criminal cases, as well as in hypothesis testing, we consider a type 1 error to be worse than a type 2 error, and the hypothesis tests are designed to minimize the probability of type 1 error. So that's very important. And again, doing the z-test calculation by hand will help you understand how it works. So I want you to be able to do it by hand and as well using StatCrunch. This is the only hypothesis test that you'll have to do by hand. And there are example videos I made to show you how to do both. So please watch them as well. And if you have any questions, let me know. Thanks.